In the century-long history of automotive development, there is a logic deeply ingrained in our intuition. If you want to save fuel and achieve high efficiency, you must precisely control the engine's RPM. And the most direct and core mechanical device to control RPM is the clutch and multi-gear transmission. When we drive a traditional fuel car cruising on the highway, we naturally shift into the highest gear. Through the gear ratio amplification inside the transmission, the wheels can sprint at extremely high speeds, while the engine can steadily remain in a low RPM range of over 2,000 revolutions per minute. When encountering a red light or needing to coast, step on the clutch to sever the physical connection between the engine and the wheels, allowing the car to glide forward using inertia. At this time, the engine only needs to maintain an idle state of 800 RPM, consuming a minimal amount of fuel. This behavior of reducing RPM by shifting gears and cutting off power through the clutch is an absolutely correct physical law in the world of fuel vehicles, and also the fuel-saving secret revered by every veteran driver. Therefore, when the era of electric vehicles arrived with overwhelming force, accompanied by the range of anxiety that plagues everyone, an extremely intuitive and seemingly the impeccable question was born. Since electric cars are so afraid of running out of power, why don't engineers equip electric vehicles with a clutch and a multi-speed transmission? During high-speed cruising, lower the motor's RPM. Going downhill or coasting, stepping on the clutch to cut power and glide. Wouldn't this significantly reduce power consumption and double the range? This idea is completely reasonable intuitively, but in the underlying logic of physics and engineering, it is a thoroughgoing disaster. To fully explain this, we must first ruthlessly strip away the traditional internal combustion engine's fig leaf and see why fuel cars absolutely need a clutch. The internal combustion engine, the fuel engine we are familiar with, is essentially an extremely inflexible power source. It has two fatal physical flaws. The first flaw, it is completely useless at low RPMs. The engine must rely on the up and down motion of pistons, the cycle of intake, compression, ignition, and exhaust to generate power. If their PM is too low, for example, below 800 RPM, the engine cannot even maintain its own operation. It will violently shudder and stall. In other words, the engine's RPM can never be zero. However, when a car is stopped at a traffic light, the wheel's rotational speed must be zero. To reconcile this contradiction where one cannot stop and the others must stop, humanity invented the clutch. The clutch is like a sliding friction disc. At the moment of starting, it allows the spinning engine and stationary wheels to make a semi-frictional, hard-to-hard contact, slowly transferring the power. Without a clutch, a fuel car cannot start at all. The second flaw, the internal combustion engine's peak thermal efficiency range is extremely narrow. The engine of a typical family car usually only maximizes the energy from burning gasoline when it is between 2,000 to 4,000 RPM and at a moderate load, achieving roughly a 30-something% thermal efficiency. Once the RPM is too high, the extreme friction between the piston and the cylinder wall generates immense heat, and the intake and exhaust systems face enormous resistance, causing fuel consumption to increase exponentially. To keep the engine comfortably forever within this narrow sweet spot, we have to stuff it with a giant, bulky transmission full of various gears, using different gears ratios to act as the translator between the engine and the wheels. Understanding the helplessness of the internal combustion engine, let's turn our attention to the heart of the electric vehicle, the electric motor. Once you understand how a motor works, you'll realize that putting a clutch and a transmission on an electric vehicle is like forcing Superman to use crutches just out of fear that he might get tired from walking. It's laughable. The motor represents an era-defining, multi-dimensional strike against the internal combustion engine. First, motors simply do not have the problem of idling and stalling. Whether it is the current mainstream permanent magnet synchronous motor or an induction asynchronous motor, they both generate torque through the interaction of electromagnetic fields. The moment power is applied, even if the motor's RPM is absolute zero, it can instantly unleash 100% maximum torque. This is a revolutionary difference, since the motor 1T stall at 0 RPM and can output maximum power. Do we still need a clutch for semi-engaged starting? Not at all. In the structure of an electric vehicle, the motor's output shaft, through a set of fixed ratio reduction gears, is rigidly and directly connected to the wheel's drive shaft. When the wheels stop, the motor stops. When the wheels spin, the motor spins. No friction plates, no torque converters. The power transmission is 100% direct and pure. So what about high-speed cruising? This is the fuel vehicle mindset trap that most people fall into. Everyone assumes that the higher the RPM, the more power it consumes. So a transmission is needed to lower the RPM. To bust this myth, we must introduce a fundamental physics formula. Power equals torque multiplied by RPM. Imagine you are currently driving an electric car, moving at a constant speed of 120 kilometers per hour on the highway. At this moment, the wind resistance the car needs to overcome and the rolling resistances of the tires are fixed. This means that to maintain this speed, the total power required by the car is a fixed value. Without a transmission, the motor might be operating at a high speed of 10,000 RPM. At this time, its RPM is high, but the torque output is relatively small. Now, let's do a thought experiment. We forcefully equip this electric car with a transmission, pushing it into overdrive, bringing the motor's RPM from 10,000 forcibly down to 3,000 RPM. Will a miracle happen? Will power consumption decrease? The answer is absolutely not. It might even consume more power. Returning to the formula just now, the total power requirement is fixed. When you reduce the RPM by 3 times through gears, in order to maintain the same power output, the motor must output 3 times its original torque. In the world of electric motors, the magnitude of torque directly depends on the amount of current input to the coils, while the level of RPM primarily corresponds to voltage. When the motor is forced to output immense torque at low RPMs, the inverter must pour massive current into the motor's copper coils. At this time, another cold law in physics appears, Joule's law. The heating power of a conductor equals the square of the current multiplied by resistance. Because current has a squared impact, when current triples, the waste heat generated by the coils increases ninfold. You thought lowering the motor's RPM could save energy like a fuel car. But actually, you just turned the electrical energy that should have driven the wheels into massive amounts of heat, wasted and dissipated in the cooling system. More importantly, the high-efficiency range of an electric motor is shockingly broad. A well-designed drive motor, from 20 kilometers per hour to 120 kilometers per hour, can maintain its energy conversion efficiency almost between 85% and 95%. This is worlds apart from the narrow, pitiful, sweet spot of a fuel engine. Since the motor's efficiency at 10,000 RPM and 3,000 RPM is nearly exactly as high, why should we take the unnecessary step of installing a complex mechanical structure? Not only that, adding a clutch and transmission would also bring a devastating blow on a physical level. That is, weight and mechanical loss. A multi-speed transmission capable of withstanding the massive instantaneous torque of an electric vehicle, plus the clutch system, easily weighs 80 to 100 kilograms and is very bulky, with the electric vehicle's chassis space at a premium. Stuffing in this pile of mechanical scraps means you must sacrifice space for placing batteries. Fewer batteries, yet a heavier body. This is a double penalty in the range equation. Furthermore, wherever there is mechanical gear meshing, there will inevitably be frictional losses. Even the world's top-tier transmission will eat up about 5% of power transmission efficiency you originally wanted to squeeze out. That minuscule 1% of motor efficiency by dropping our PMIs. But as a result, the transmission itself consumed 5% directly through mechanical friction. This is known in engineering as a typical case of putting the cart before the horse. But if all of the above is just addition and subtraction in efficiency, then what I'm about to say next is the ultimate bottom line of why electric vehicles must absolutely not have a clutch. Once this bottom line is crossed, half the soul of the electric vehicle dies. This soul is called kinetic energy recovery. We all know that when you release the accelerator pedal in an electric car or step on the brakes, the motor instantly changes its role from an electric motor consuming energy into a generator producing electricity. It utilizes the vehicle's massive inertia and kinetic energy to push the motor to rotate in reverse, cutting magnetic lines to generate current and charge it back into the battery pack. This process simultaneously creates strong electromagnetic resistance, achieving a braking deceleration effect. This technology is the biggest secret behind why electric vehicles can still maintain astonishing range during stop-and-go city driving. Now, let's put the clutch back in. Imagine the driver used to a manual fuel car. Upon seeing a red light ahead or facing a long downhill slope, following years of intuition, steps on the clutch, cutting off the power, ready to let the car glide easily. At the exact moment the clutch disengages, disaster strikes. The physical connection between the wheels and the motor is completely severed. The wheels indeed roll freely on the ground, but the motor sits idly by. The massive kinetic energy of the car body originally belonged to tens or even hundreds of kilowatts, which could have been converted by the motor into precious electrical energy charged back into the battery. Now, because of the clutch disengaging, all turns into invalid coasting. When the driver eventually has to step on the mechanical brakes to stop the vehicle, that precious kinetic energy can only all turn into high-temperature heat energy of hundreds of degrees on the brake discs, ruthlessly dissipating into the air. Installing a clutch is equivalent to personally castrating the electric vehicle's most powerful healing skills for a non-existent myth of saving power by lowering our PMIs, sacrificing the kinetic energy recovery system. This, in the energy management logic of electric vehicles, is a severe crime that is absolutely not allowed. Hearing this, someone will definitely bring up a very sharp counter evidence. If electric vehicles don't need transmissions, then why did the Porsche Taycan and the Audi e-tron GT actually have a 2-speed transmission installed on the rear axle? Do top German automotive engineers not understand physics? This is a brilliantly fascinating exception. It not only doesn't overturn the previous theory, but instead further confirms the engineering limits of electric vehicles. Porsche installing a 2-speed transmission is absolutely not for saving power or increasing range. The existence of this transmission is to solve an extreme performance contradiction, the tug-of-war between 0 to 100 kilometers per hour acceleration and top speed. Although the motors RPM can be pulled very high, it is not infinite. When the motor's RPM is extremely high, an internal physical phenomenon called back electromotive force occurs. It resists the input of current, causing the motor's torque to drop sharply at high RPMs. If an electric car wants to have a violent acceleration force that kicks you into the back of your seat when starting, its reduction gear ratio must be set relatively large to amplify torque. But once the gear ratio is amplified, When the vehicle accelerates to around 180 kilometers per hour, the motor's RPM will have already approached the redline limit of 16,000 RPM, and the car simply cannot go any faster. A top speed of 180 kilometers per hour is more than enough for a standard family commuter car, but for a car wearing the Porsche Shield emblem, meant to battle traditional supercars on the unrestricted German Autobahn as a pure electric sports car. This is an unforgivable disgrace. Therefore, the solution from Porsche engineers is to stuff a comprisely-sized speed transmission into the rear axle. First gear has an extremely large gear ratio, dedicated specifically to executing launch controls, creating astonishing 0 to 100 acceleration times. When the vehicle speed breaks through 80 or 100 kilometers per hour, the system instantly switches to second gear, making the gear ratio smaller. This switching action is not to let the motor enter some power-saving range, but simply to forcibly pull the motor's RPM down, giving it room to continue climbing higher, so that the car's top speed can be pushed all the way to 260 kilometers per hour or even higher. So, the Taycan's two-speed transmission is a product of performance compromise born to break through high RPM physical bottlenecks. It brings the ultimate handling limits, and the price is added weight, complexity, and undeniable mechanical loss. And even the Taycan with 2 gears does not have a traditionally defined clutch pedal for the driver to control. Its gear shifts are entirely completed automatically by the computer within tens of milliseconds, still maintaining uninterrupted power. Returning to the vast majority of electric vehicles, we don't have Porsches. Paranoia for a top speed of 250 kilometers per hour. What we truly need is high efficiency, smoothness, and reliability. So, without a clutch and gears, how exactly do electric vehicles achieve extremely delicate power control and energy conservation? The answer lies hidden in a mysterious black box with no mechanical gears that can be called the true soul of an electric vehicle, the inverter. The inverter is the electronic transmission of the electric vehicle era. We know that what is stored in the battery pack is direct current DC, while the motor driving the wheels is usually a 3-phase alternating current AC motor. The core job of the inverter is to convert DC power into the AC power needed by the motor. But it's not just as simple as conversion. It is more like a super DJ with extreme hand speed. Inside the inverter of a modern electric vehicle, it is filled with components called power semiconductors, such as the historically mainstream IGBT and the ultimate black tech that major automakers are flocking to now, Silicon Carbide SiC components. Engineers use a technology called PWM, which is pulse width modulation, to control these semiconductors when you lightly press the pedal, needing just a little bit of power to maintain moving forward at 30 kilometers per hour. The silicon carbide switches inside the inverter will turn on and off at speeds humans cannot fathom, up to 10,000 or even 20,000 times per second, through extremely precise control of the tiny time difference of each connection and disconnection, which is adjusting the width of the pulse. It sculpts a perfect sine wave current. However much power you need, the inverter, with microsecond precision, slices the exact right amount of electrical energy from the battery and sends it to the motor, absolutely not wasting a single bit. No matter how fast a traditional mechanical transmission shifts gears, the top-tier dual-clutch transmission still takes tens to hundreds of milliseconds, and it only has 6, 8, or 10 gears. The power output curve is forever stepped, but with an inverter made up of semiconductors, its control accuracy is at the microsecond level. The voltage and frequency changes it provides to the motor are infinitely continuous. The inverter can constantly, at a frequency of tens of thousands of times per second, based on your pedal depth and vehicle speed, and even the tire's grip. Dynamically calculate and adjust the optimal electrical waveform for the motor. This is like a god-tier transmission with infinite gears that can always make the motor operate in the most comfortable and efficient way. With such a powerful, almost sci-fi level chip-based power distribution system, why would we want to rely on a set of mechanical gears and friction plates that weighs 100 kilograms, reacts sluggishly, and generates frictional heat energy? The history of fueled cars is too glorious, so much so that we mistook the clutches and transmissions, invented to solve the flaws of the internal combustion engine, as a natural standard feature of automobiles. We are accustomed to hearing the rise and fall of engine RPMs, accustomed to that slight jerky feeling when shifting gears, and equating these with driving pleasure and fuel efficiency. But the underlying logic of electric vehicles is a thorough revolution. It replaces the explosion of pistons with pure electromagnetic fields and uses the microsecond switching of silicon wafers and software algorithms to replace the physical meshing of metal gears. It no longer needs complex mechanical devices to mask its own inadequacies, because the motor itself is an almost perfect power converter. The reason why electric cars absolutely refuse to use a clutch to adjust RPM is because under the dual multi-dimensional strike of physical laws and semiconductor technology, that mechanical mindset from the old era has long lost its meaning of existence. True progress is often not about continuing to pile structures onto the old framework, but erasing the very problem you originally wanted to solve. Completely from the stage of history together. Completely from the stage of history together.